All right, so chapter 5 focuses on transfer function modeling of dynamical systems. We're going to go through some introduction. We're going to talk about some comments on transfer functions, and then we're going to go through several example problems. And then the last part of this chapter will cover a little bit of block diagrams. Okay, so the transfer function of an LTI system, and that stands for linear time invariant. So the transfer function of an LTI system is defined as the ratio of the Laplace transform of the output to the Laplace transform of the input under the assumption of zero initial conditions. So if we have an LTI system defined with the following differential equation, we have some constant A0 times dn y over dtn. So this is the nth derivative of y with respect to time, plus some a1 times dn to the minus 1 y divided by dt to the n minus 1 plus an minus 1 y dot, so that's our first derivative with respect to time, plus an y. This is n equal to some input of x, or b0 times dm applied to x, dt to the mth, so the mth derivative of x with respect to time, plus some b1 d to the m minus 1 x over dt m minus 1 plus plus m minus 1 x dot plus b sub m x. So in this equation, y of t is our output and x of t is our input. And so we have a bunch of derivative terms added together for y is equal to a bunch of derivative terms of your input and the input itself. Okay, so to find a transfer function, we're going to take the Laplace transform of both sides. We'll then divide the, let's see, what did I say? We're going to then divide, hold on a second. We're going to divide the Laplace transform of our output. Yeah, hold on, there's a mistake here. All right, we'll just write it out. So our transfer function TF is going to be equal to g of s. We'll often use either a capital G to represent the transfer function. Other times you might see an H, a capital H used. This is equal to the Laplace transform of y of t divided by the Laplace transform of our input x of t. And here we're assuming that we have zero initial conditions. So this is going to be n be equal to big Y of s divided by big X of s. and it's going to be equal to a very large fraction of polynomials in S. So in the numerator, we're going to get b0, s to the m, plus b1, s to the m minus 1, plus dot, plus b, m minus 1, s, plus bm. And then likewise in the denominator, we're going to get a polynomial in s with all of the a coefficients. So a0, s to the n, plus a1, s to the n minus 1, plus dot, plus an minus 1, s plus an. Okay, so the benefit of transfer functions is it allows us to represent the system dynamics using algebraic equations in S. This is exactly what we just did in the previous example. We're now just kind of formalizing this. Secondly, if the highest power in the denominator of that transfer function is n, then we'll say that the system is of nth order. So when we say the system is a second order system, means the highest derivative is a second derivative, and then in the denominator of our transfer function, we'd expect to see an s squared. All right, so we're going to go through some comments on the transfer functions. First is that this analysis is only applicable to systems that are governed by linear time invariant differential equations. So any kind of nonlinear system or any kind of equation that has time varying parameters or coefficients, this analysis is no longer valid for that. It's used extensively, or transfer functions are used extensively in analyzing many systems across many different industries. When you go to do controls, this is basically what you'll be dealing with, is looking at transfer functions and then doing block diagram algebra in order to find the transfer function of the whole system. All right, with that, we're going to write out a couple very important comments for transfer functions in general. First is that the transfer function of the system is a mathematical model for the system that relates input to output. And so that's what really matters here, is that it's relating the input to the output. So we'll just say the transfer function, or TF, of a system is a mathematical model for that system that relates input to output. So second is that the transfer function is a property of the system itself. It does not depend on the magnitude or the nature of the input. And that means that the transfer function itself captures the dynamics of the system. It is the dynamics of the system. So we'll say then that the transfer function is a property of the system itself. And it does not depend on the magnitude and nature of the input. Okay, so third is that the transfer function automatically takes into account the units of the system, but the unfortunate thing is that it doesn't tell you anything about the physical nature of the system. And what that implies is that we can get the same transfer function for totally different physical systems. You could get the same transfer function for electrical system as you do for some mechanical structure or some thermodynamic system. It all depends on what you find for the transfer function. So the transfer function automatically takes into account units. That's the first thing we'll write. So it automatically takes into account, or takes units into account. But it does not tell you anything about the physical nature of the system. It does not tell us anything about the physical nature of the system. Okay, so our fourth comment is that if the transfer function is known, then the output can be studied for various forms of input with the goal of trying to understand the physical nature of that system. So if the transfer function, or the TF, is known, then the output can be studied for various forms of input with the goal of understanding the nature of the system.
When you say that various forms of input, does that account for the current state and also like additional control inputs by the joystick?
So we're not thinking about control just yet with this, but think about, what if we apply a unit step to the system or an impulse or some combination of those? How does the response change and how does the transfer function change? All right, and the last thing we'll say is that if the transfer function is unknown, then it can be determined experimentally by applying some known input and then measuring the output. So say that if the transfer function is unknown, it can be determined experimentally by applying known inputs and measuring the output. All right, we're going to go through two examples. I'm going to solve one example, and then you guys are going to solve the second example. And let me fix a typo up here. So for the example shown here, we're considering a simple harmonic oscillator with some generic external force. The system here is governed by the following equation of motion. This is just our standard harmonic oscillator, mx double dot plus bx dot plus kx is equal to f of t. We're asked to just determine the transfer function for this system. We're just going to take the Laplace transform of both sides, and then we're going to directly solve for our transfer function. So we have the Laplace transform of mx double dot plus bx dot plus kx equal to the Laplace transform of f of t.
Is there a reason it's B instead of C?
So the question is there a reason why we have b for our damping coefficient? There's not a reason. Typically, you either use C or you use B, and sometimes you'll see a D there as well. People tend to avoid using D. Well, first of all, D kind of makes sense because it stands for damping, but you tend to avoid using D because derivatives are represented with D's as well, and that can get confusing. But yeah, B or C doesn't matter. So take the Laplace transform of both sides. We're going to get here ms squared plus bs plus k, all of that multiplied by big X of s. And here we're assuming 0 initial conditions, so none of the initial conditions show up because they're all 0. And that's then equal to f of s, where again f of t was our just generic forcing function. We said earlier that g of s Our transfer function is equal to the output of the system divided by the input, or Laplace transforms of those. The output of the system in this case is x of s. So we'll get x of s divided by our input, which is that big F of s. And so we just need to take the equation that's shown on the left and put that into a form where we can find this g of s. So our g of s is going to be equal to, again, big X over big F of s. So we're going to divide that top equation, or that middle equation, we're going to divide both sides by big F of s, and then we're going to bring everything in the square brackets on over as well, and then we're going to get 1 divided by ms squared plus bs plus k. And that is the transfer function for a harmonic oscillator. Yeah.
Is this assuming zero initial conditions?
Mm-hmm. Yeah.
Just to confirm my understanding, when we say zero initial conditions, it means the initial conditions are all zero, not that we just don't have them.
Yeah, they're all zero. They're exactly zero. Yeah, they're not. It's not that we don't know them. They're zero. Period.
Okay.
Yeah.
Thank you.
Yeah. And then, by the way, if you let s equal to j omega, you'll find that g of omega is equal to, if we plug this in here, we're going to get k minus m omega squared plus j times b omega, 1 over that. And then this is well, really the frequency response function, and it relates back to what we did earlier in this class. And then you would take the magnitude of this, and then you would end up finding exactly what we found when we studied steady state response, and then also when we studied resonance. You can relate this all the way back to that as well. Yeah, we'll come back and look at this stuff in green later when we go back to frequency response functions. We'll move on. So we're going to take the Laplace transform of both sides. This is going to give us Laplace transform of m y double dot plus b y dot plus ky is equal to the Laplace transform of b u dot plus k u. This will give us ms squared plus bs plus k times big Y of s equal to bs plus k times a big U of s. And then from here we can find that the transfer function is equal to big Y divided by big U. It's then equal to bs plus k divided by ms squared plus bs plus k. Okay. Okay, so we're going to move on and we're going to look at what is known as the impulse response function. And then we have a longer example before we get to, which we'll probably finish next week, but we'll start today. So the impulse response function, or if we have a transfer function of a system, we'll say g of s equal to y of s, that's our output, divided by big X of s, which is the input. Then we can go and solve for our output, big Y of s, as being equal to the transfer function g of s times the input, big X of s. And so in this regard, we can think of the transfer function as being a function that transfers the input into the output. Hence why we call it transfer functions. If you take the inverse Laplace transform of g of s, or the transfer function itself, you'll get what we call the impulse response function, which is just the response of a system to a unit impulse applied to it. And so you could find then the transfer function by experimentally exciting your system with an impulse and then measuring the output of it. And so in a vibration problem, you take a hammer and you hit a structure with the hammer, and you measure the input from that hammer, and then you compute, generally you do this in frequency domain, but you would compute the frequency response function or the transfer function with respect to that impulse that you've applied by the hammer. Okay, we've got a third example here. We're considering an oscillator shown here that's governed by, in this case, there's two equations of motion. There's one governing the displacement of the oscillator, which is mx double dot plus k1x plus k2 times the quantity x minus y. And then there's an external force, P of t, acting on this system. And then there is a second equation for y here, which is b2 times y dot plus k2 times the quantity y minus x, and that's equal to 0. We're asked to determine the transfer function for this system for assuming generic parameter values, and then some generic input p of t. And then in part B, we are given numerical values and what that forcing function is. And we're asked to compute the analytical solution for x of t. And so for this example, I'm going to have you guys work on it as well. And we'll spend the rest of the class working on this example.